Okay, we should get started. Right, good morning. Welcome to this very special lecture. Um, I've been requested to give a lecture on Introduction to Quantum Information Science. My name is Kotik Singh, and as is customary for anyone with a Chinese heritage, we put our surname, the family name first, right? So Ko is my surname. Um, and so my name doesn't look very familiar because it's not in Hanyu Pinyin. And but for those of you who come from Fujian, you might recognize that Xu Decheng, which is also my name in Chinese, is when read in Minnanhua, is called Tek Sing. So that's the origin of the typical Chinese names in Singapore, because I think our heritage comes from southern China for the Chinese Singaporeans in Singapore. And we use the regional language sounds when we translate that name into English. Okay. So I'm senior lecturer in physics at the School of Physical and Mathematical Sciences at Nanyang Technological University. At first, I thought I was going to give a lecture in person, okay, but I understand from the organizers that all of you are still in China. Is that right? You are not in Singapore yet. Okay, feel free to, if I ask questions, feel free to unmute or just type in the chat or give a thumbs up. There are emojis that you can use, including a raise hand emoji if you want to ask questions. Although for me, I only have one screen. I don't have two screens. I'm not in my office today. So it'll be hard for me to see the emojis. It's easier if you type a question in the chat. You could type it in English or Chinese. I would understand both. Okay. Okay. So let me begin. So let me see. Let me just. Okay. To begin with, when I was asked to give a talk or a lecture titled Introduction to Quantum Information Science, I was wondering where to start. Okay, because quantum information is now a very broad field. You could look at quantum information science from the perspective of information theory, and that would be a lot more mathematical and computer science. Okay, and those things are not quite my training because as you know, I'm a lecturer in physics, so I'm trained in physics. So we could then go the route of looking at quantum mechanics. Okay, but if you were to just look at quantum theory itself, it tends to be very technical. Uh, or we could look at quantum technologies, right? The technologies that actually China is very much ahead in particular in quantum communications. Okay. So I grappled with what this introduction how to scope this introduction, and I thought, let's go to the basics. How did this broad field of quantum information science and all the quantum technologies that have come forth, how did this come about? Okay, so I wanted, therefore, to give you an introduction to the foundational questions around around quantum theory so that we know whether or not quantum information science and quantum technologies are founded on strong evidence. Okay, we'll see if I succeed in doing that. Okay, so let's get started. Now, I actually have a lot of slides. Okay, and hold on a second. Give me a second. Okay. So I actually have a lot of slides. I have 120 slides and it's 2 hours. All these slides came from my course that I teach at the third year level, called Open Quantum Systems. So there will be technicalities, which I will gloss over because the technicalities I took one semester to complete. So I really hope to give you a flavor of the questions I want to answer and not too much of the technical details. Okay, so if we talk about quantum information science and the technologies that have come forth, you could um, classify the technologies into three types of applications. Okay, all of them are founded on quantum theory for sure. Okay, the three applications. The first is rather is in between the mature and emerging stage called quantum sensing, where you are trying to measure with quantum systems, uh, say fields or quantities that are ultra precise. Okay. The second, which China is actually a world leader in, is quantum secure communication. So this lock represents the high security, and it's very much driven by worldwide by the need for secure encryption. Okay, and this kind of communication is supposed to be absolutely secure. Also, the claim goes. So much so that it's even secure against what is called a quantum computer that can hack into current uh, RSA encryption systems. Okay. If all this sounds um, new to you, just know that for quantum communication, one application of which is quantum key distribution, it works because if you have an eavesdropper, someone who takes some bits of information as it travels from A to B, it leaves a trace. Okay. And that's because of the fact that when you measure a quantum system, you invariably disturb it. Okay. And if you use one of those protocols of sharing this key called ACID-91, you will get a truly random shared key. Okay. And these are the result of the inherent randomness that quantum theory says is part of nature. A quantum computer is powerful because of the kind of algorithms that it runs, one of which is called Shor's algorithm, and that's the one that actually catalyzed or kickstarted all this quantum race. Shor's algorithm, at its heart, works because the superposition of quantum states, okay, where a bit can be a 0 and a 1 at the same time, okay, allows a massive parallelism where one register can hold all values at once, so-called, so that this other algorithm called quantum Fourier transform can then extract certain values via some kind of constructive or destructive interference. So what is the point here? The point is it works because of what we call superposition in quantum mechanics, where you can have a bit that is both 0 and 1, unlike a classical bit that is either 0 or 1. And finally, quantum sensing works because you can actually uh, um, sense or measure a physical quantity that is at a precision better than what a classical probe can do. Okay, and that's because of entanglement. Again, entanglement of, say, quantum systems is at the heart of quantum mechanics. Okay, so these ideas of superposition, fundamental randomness, entanglement, and so on, they all reside in quantum theory. Okay. But as you know, a theory is only good, a scientific theory is only good if there is evidence that it is true. So on what basis can we take these ideas to be true? So this is the big question that I hope to explore with you in today's short talk. Okay, so the questions we want to answer are these, okay? Despite the success of quantum technologies we see today, what are the problems with quantum theory? Okay, and that's epitomized in Richard Feynman, Nobel laureate in physics. He says, I think I can safely say that nobody understands quantum mechanics. Okay, I think more of us do now. Maybe not so much that we really understand, but that we have come to accept quantum mechanics. And is this theory called quantum mechanics just a set of calculational rules, or is there something deeper? Because David Mermin, also a famous physicist, he says, if I were forced to sum up in one sentence what the Copenhagen interpretation says to me, that's the interpretation of quantum mechanics, it will be shut up and calculate. Shut up meaning don't ask questions, but the calculations will just give you the so-called right answers. And finally, a deeper question, right? As this second question suggests, what is the picture of the physical world that quantum theory gives us? Because Niels Bohr, one of the founding fathers of the theory, says that everything we call real is made of things that cannot be regarded as real. What is reality, right? But Einstein, to him, likes to think that the moon is there, even if he's not looking at it. Okay, so profound questions. I don't know if we can really answer it, but we can shed light on why these questions come about. Okay. You might be familiar with some of these people. These are the so-called architects of modern physics and quantum theory. I took this from a book. Several Nobel laureates here, but you might know Schrödinger, Dirac, Planck, Einstein, of course, de Broglie, Born, and that's Heisenberg, I believe. Yeah. Okay. So these are people familiar to you. And actually, I'm going to use a certain notation we call Dirac notation. And before I go on to the next slide, I wanted to know whether you are familiar with this notation that I just talked about, Dirac notation, or sometimes called bracket notation. I wrote that in the chat. If you are familiar, can you please put a thumbs up emoji? If you're not familiar, thumbs down. Let me wait for you guys to respond. Do you all know how to get the thumbs up, thumbs down emojis? Is there? I wonder if there are these emojis available to you. I don't see anyone doing that, so maybe it's not available to you. Okay. Or oh, okay, it is, right? Some of you have put thumbs up in the chat. Okay, that's excellent. Until I see a thumbs down, I'm going to really assume that all of you understand what is the Dirac notation. Is that okay? Okay, not okay, put a thumbs down, okay? Okay, so let me continue then, because I probably have a lot to share. So you might be familiar with some of these things, right? Einstein talked about the photoelectric effect and much more. Broadly about the wave-particle duality. I'm going to talk about Born's rule and Schrödinger's cat, okay? And of course, Dirac notation. Heisenberg comes in, I think, rarely, Compton not. But besides these people that you're familiar with, Oh, okay. So let's start with Schrodinger's cat. So this epitomizes one of the problems with quantum theory, right? Because in the Schrodinger's cat problem, I wouldn't call it a paradox. You have a quantum system. This is a radioactive particle. So it is a quantum system that quantum theory can say, can describe it as being in a superposition of both decayed and not decayed. Okay. And some some contraption links this state of the radioactive particle to whether this hammer will drop or not drop. If the hammer drops, it breaks open a poison vial or vase. The poison kills the cat that's in the room. If it doesn't, the cat stays alive. So quantum theory says that if your quantum system is interacting with another system, then through this cascade of interactions, you must, since the cat is made up of a collection of many quantum particles, right? Um, so you must then describe the cat as also being dead and alive if your radioactive particle is also in that superposition of decay and not decay. So to Schrodinger, that's the implication of quantum theory, and that troubled him. Okay, so there is no real resolution, but there are steps towards a resolution. But before we got to the resolution that we think is the consensus today, people like Eugene Wigner, a famous physicist as well, thinks that, oh, maybe you have to invoke some kind of reference to consciousness, which actually we don't have a theory about. Okay. And maybe because of language, right? We talk about observables in quantum mechanics. Uh, Observations have to be performed by a person. So someone like Pascal Jordan think that actually the act of observation, instead of showing up what's being measured, they produce actually the measurement. So these are very unphysical ideas, and they give rise to a lot of what I call and what is called new age mumbo jumbo. Okay. Then you have on the internet quantum healing and all these unfound claims without basis, but they sound very nice. They sound like deep and appealing to people. Okay, so those people you have seen before, I'm not sure if you have seen these people before, and these people will form the the work of these people will form the basis of what I'm going to talk about. There's this book called Quantum Dissidents. Okay, they rebelled against the standard interpretation, and they made progress. The first of this is John Bell. Okay, you will hear about Bell's theorem. Um, this guy is David Bohm. Okay, and then maybe these two are a bit more famous. You can see they are in black and white. They have already passed on. Zay, I believe, is still around. Okay, not so famous in the sense that his name has not made its way to standard physics textbooks in university yet. But Zurek has been very active in the field of quantum foundations. Okay. And where these people come in are in the 1950s and later, right? You can see that in the last 70 over years, there has been work to try to put quantum theory on a firmer footing. Okay, from David Bohm with another interpretation in terms of hidden variables, Bell on his Bell's theorem, which he titled in a paper on the EPR paradox. E, P, and R, you also see them, Einstein, Podolsky, and Rosen. These four people, they are not here. They did some very good experiments. And Zay again on interpretation, Zurek, and then as Elaine Espay and so on. Okay, and because of the work up to the 80s and 90s, now quantum technologies is very much uh, well, I wouldn't say very much. It's now at a developing and mature stage. Now, first of all, I want to start with this quote. Quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. If you know what a Hilbert space is, it's an abstract vector space. It's a mathematical abstraction where quantum states are thought of as vectors in a linear vector space, right? With a certain inner product and so on. So by saying this, I think what Asher Perez is trying to pin down is the fact that you need to have experimental or empirical evidence for your theory. Okay. So what is this theory? Now, I won't go through the full theory of quantum mechanics, but I'll pick some interesting ones that are relevant for today's talk that is trying to answer the questions we just talked about. One is the spectral theorem, okay? So these are the technical details that if you don't get, it's fine, okay? Just remember at the back of your head, okay, there's this thing called spectral theorem, it's important. Okay, what's the spectral theorem? If you have an operator that has this property called being self-adjoint, okay, that means if your operator is a matrix, the transpose and complex conjugate of itself is the original matrix. If you have a self-adjoint operator, then it can always be written, since I say it's a matrix, in a diagonal form. That means there are only diagonal entries. And how to read this notation? This is a bracket notation or Dirac notation I'm talking about. This notation means that this is the column and this is the row of the matrix. Okay, so the jth column, jth row means that is on a diagonal. So the diagonal elements on the matrix will contain eigenvalue, and this eigenvalue is real. Okay, so there is such a spectral decomposition. You can always diagonalize a self-adjoint matrix or self-adjoint operator, and it will have real eigenvalues. Okay, so that's just some technicalities. By the way, all quantum mechanics observables, they are Hermitian. Okay. And then the consequence of this means that if you have two observables, A and B, for example, I want to look at, say, momentum and position, or momentum and energy. These are things I can measure. We call them observables. If they commute, okay, this square bracket means that it's a shorthand notation for saying I look at the things in the square brackets. I use this to mean A times B minus B times A. So in other words, the order is flipped in the first and second term. And if AB minus BA is 0, right, that means the order doesn't matter. We call this as commuting. If A and B commute, then there is a common set of eigenvectors. Okay. And that ties in with your spectral theorem before, because these are eigenvectors, these VJs. Okay. And they can always be chosen to form an orthonormal basis. Okay. And if you have A and B commuting, they have a common set of eigenvectors. Okay. So keep those two things in mind. And then we come to Bond rule, which is that if I have a quantum state that I say is in some superposition of 0 and 1, where 0 and 1 represents two distinct and orthogonal states of the system, then the probability of finding a 0, let's say, is just modulus squared of A. Okay, where did this come from? It came from Bond. This is called Bond's rule. And he published it in German. So this is a translation from Google. And he titled it on the quantum mechanics of collision processes. Okay, and it's just a footnote in German. So this footnote 1 says that, okay, the wave function, which was written in terms of the position basis x, okay, closer consideration shows that the probability is proportional to the square of the function. So Bond's rule, which is so central to quantum mechanics, is just a footnote in a paper. There's no reason why he just puts it there, and that's what it is. Why are these three things important? And that's because they are related to how the measurement postulate of quantum mechanics. Okay, now all these things come from my notes in my course. The only thing I want you to take away from is this, right? That when you do a measurement according to the von Neumann scheme of measurement, the state goes from psi to some other state. And this some other state is defined by your measurement operator, and then divided by this number is a real number. So it's just to be renormalized to 1. How do we see this? So if we go back to the original superposition of 0 and 1, and I'm using a measurement operator that is just a projection onto 0, okay? Then this is true, okay? It's not totally true, okay? This gives you A. Okay, so I should put an arrow instead. This gives you A, but when you divide by A here, okay, you get a fully normalized state, okay? So measurement kind of what we call collapses the state into either 0 or 1, okay? And what is the connection between the three things I talked about? The connection is here. The result of a measurement of a physical observable is one of its eigenvalues, okay? Physical observables are represented by Hermitian operators. That's the statement from spectral theorem. Okay, so you get one eigenvalue and you get an eigenvector. If the measurement of the observable is made many times, then you can get an average, and the average is obtained by Bond's rule. Okay, so you have the orthonormal basis. You can express the state in that basis. It's just mathematical, and Bond's rule tells you that to find the state K, the probability is that coefficient squared. And the first postulate tells you the system will collapse into one of the eigenstates of the observable. Okay, so these are how these three things are linked together. So it's self-consistent as a theory, and this is what is being observed. Okay, that whenever you do a measurement, you just see an eigenstate of the physical observable. You don't see a superposition. Okay, so let me skip the details. So that's the idea of measurement. And when you look at it, when you calculate the dynamics of or the time evolution of a quantum system, it obeys this Schrodinger's equation. I don't want to go through the details again, but H represents the Hamiltonian that governs the time evolution. U is a unitary operator or a unitary matrix that tells you how the state progresses. Okay, the point here is this time evolution is unitary. That means it can go forward and backward in time, but measurement is non-unitary. It's just collapsing a quantum state. Okay, so you can go forward, but you can't go backwards. So the theory is uses two different descriptions of time evolution. One for when you are not measuring, one for when you are measuring. So you can say, okay, there's some inconsistency in the theory at best, but Einstein went further to say maybe it's incomplete. But we can also ask the question, why must a theory be consistent in this way? Because that's imposing our view on how to describe nature. So keep these thoughts in mind. Two ways to this, two time evolution processes for the same theory. Okay, so that's Asher Perez, and to him, okay, this is again from his textbook Quantum Theory. To him, quantum mechanics is, in a strict sense, just a set of rules allowing the computation of probabilities for outcomes of tests. He calls tests, which are experiments, that follow specified preparations. Okay, how you prepare the state, how you let it evolve, and how you measure. But if it's just a set of rules, it seems to be a shallow and superficial um, theory, because when we want to understand the universe, let's say, or the world around us, we want to understand it in terms of what's deeper than what we see. We don't want to understand it in terms of, say, oh, here are a set of rules, and you can do a lot of calculations. So is this formalism, the mathematical formalism of quantum mechanics, really just an instrument, or does it reflect deeper reality? Okay. Just to reiterate, right, if A and B commute, they imply a common set of eigenvectors. The converse is true. If they do not commute, you can never find a common set of eigenvectors. So for the next thing I want to talk about, remember this. So what does not commute? Position and momentum don't commute. If you measure the spin of an electron in the z direction, that doesn't commute with the spin measured in the x direction. Okay, so keep that in mind. And that's important to understand the Stern-Galat experiment. Okay, so Stern and Galat found that if you shine a beam of silver atoms, which possess a magnetic moment, and you shine it through an inhomogeneous magnetic field, okay, so it's not uniform, you should, in classical theory, be able to find the force on the magnetic moment of the atom. Mu is the magnetic moment. B is the field that it is in. And this force is just the negative gradient of the magnetic potential energy. So this is a semi-classical idea, right? You have potential energy, and negative gradient of potential energy gives you a force, right? It's quite established in classical mechanics. And if the magnetic moment mu is a constant, then the force depends on the the magnetic field gradient. And there is a magnetic field gradient because this is non-uniform. Okay, and therefore, if I have the idea, okay, a magnetic moment is just a North Pole, South Pole. So the North Pole, South Pole, they can, like a bar magnet, they can point in any direction. Doesn't need to be this way, could be to the left, could be this way, could be down. There is a solid angle of directions. But if you want to talk about a plane, there's a 360 degrees of directions. So the expectation is that you should get, number 4, a line, right? Those that are pointing up, or, it goes all the way to the top. Those that are pointing down goes all the way to the bottom. Those that are pointing in between, left, right, or some angle, you will get a smooth variation. But Stern and Galat found that there were only 2 spots. Okay, this was the original plate, photographic plate. They sent this to Niels Bohr. Okay, and based on this result, then we can say, oh, okay, then maybe in this beam, you get some quantization of magnetic dipole moment. There's a vector that only points in the plus z or minus z. But because we think of a vector as pointing in a direction in space, right? We can also think about how to measure the x and y directions. Okay? Here, this is just a confirmation that if you put it through 2 sequential Stern-Galat apparatus, both measuring in the z direction, you still get your z when you block your, you still get your z plus when you block your z minus after the first one. But the sequential Stern-Galat experimental results are these, okay? If you block the z minus, and for the next one you measure in the x direction, you will get 2 possibilities. Again, quantization, x in the plus and x in the minus. So you can then think about, oh, the beam that traveled through here, z plus, z minus, had a dipole moment vector that was pointing in the plus z and plus x. This guy, this set of this atoms in this beam that emerge points in the z plus and x minus. Now, if you put another one after that, where the apparatus measures in the Z direction, and you block this one, you expect that you get Z plus and X plus atoms in this beam, and what comes out should only be Z plus, but you get both Z plus and Z minus. So this was this is an issue because we then kind of think about the filtering of the filtering function of these sequential apparatus. That idea of filtering out certain directions is then faulty. But the standard quantum mechanical treatment, allows you to do that. Okay, because your spin measurements, they are operators or they are matrices. Okay, when they are acting on their eigenvectors, you get just the eigenvalues with the eigenvectors unchanged. So if you had measured Z plus here, the beam here has collapsed into an eigenstate Z plus. And then you measure it again, right? You get Z plus again, it was unchanged. Okay. And there's nothing special about the Z-axis. You can do the same mathematics for the X and Y-axis or for some arbitrary direction that I call N. Okay. And N, right, as spin in the N direction can be written this way with the polar and azimuthal angles in spherical coordinates. Okay. And it's not difficult to understand the Stern-Gerlach experiment in this sense because in standard quantum mechanical language, you can always express an eigenvector in terms of another set of eigenvectors in another basis. So the Z plus is a linear combination of X plus and X minus. So that makes sense when you see the beam that goes through, Z plus goes to, when you measure with the X direction apparatus, goes to X plus and X minus. Okay. And X plus and X minus are just combinations of Z plus and minus. Okay. So the interpretation is this, that when one of the beams is measured, the prior measurement has erased all information. Okay. In other words, the observables X and Y, X and Z are incompatible, or we can say that they don't commute. And you can check that with the matrix commutation. Okay, so Dirac then says that whenever a system is definitely in one state, we can consider it as being partly in each of the two or more other states. In other words, a superposition. And the superposition can be in a different basis. And this is something that cannot be conceived on classical ideas, right? So the idea of filtering out certain directions, that's classical. Superposition and measurement is not. So why do we go through all these technicalities, right? We went through all these technicalities to come to a conclusion that incompatible observables limit what we can say meaningfully. We had a spectral theorem that you can always find a complete set of simultaneous eigenstates for compatible or commuting operators. And the converse is also true. You can never find simultaneous eigenstates for incompatible observables, in which case I try to impress upon you that Sx and Sz are such a pair. It means that you cannot speak meaningfully of simultaneous eigenvalues of Sx and Sz, even though we can measure each observable in separate experiments. Okay. In other words, you cannot think of this property called magnetic dipole moment. You cannot even visualize that as a vector in 3D space, because if you visualize its X component, you cannot visualize its Z component. You're kind of forbidden by quantum theory because it's not meaningful. Okay. If you visualize that this is pointing in the Z direction, you should not think about you should not be able to think about it pointing in the X direction, let's say. So you should not imagine this picture, but our entire experience, right, based on the macroscopic world, allows us to think about this picture. And therefore, Niels Bohr said there is no quantum world. You shouldn't be able to imagine those things. There is only an abstract quantum mechanical description. Abstract would be, I guess, mathematical, based on Hilbert spaces, matrix multiplications, and so on. And therefore, it is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. So Niels Bohr has then limited what we might have unintentionally desired. We wanted to find out what's the meaning of it all. Is there something deeper beyond the theory? And he's saying, no, no, no. The theory is just theory, it's abstract, but there's nothing under the theory, or it's not even meaningful to think about what's under the theory or what the theory is trying to describe. And that disturbed Einstein. Okay, so this no quantum world, no quantum picture, right? What picture does that mathematical formalism give us? First, we know quantization. I don't want to go through that. We just talked about incompatible observables. We didn't quite talk about fundamental randomness, but let me just quickly give a idea to it. If you have, so let me go back a few slides. Right, if you were in Stern and Gerlach's time at the turn of the 20th century, they could not produce single particles, right? It was a beam of silver atoms. But if you know what we know today, and we are able to, let me go back to that. Yeah. And if you are able to now prepare a single particle, a single silver atom, okay, say pointing in the Z direction after one Stern-Gerlach apparatus, then is in a superposition of X and X plus and X minus. The fundamental randomness idea in quantum theory says that it's impossible to determine which outcome, X plus or X minus, will emerge. It's fundamentally random. Again, this disturbs Einstein, right? Because to Einstein, what we cannot say about a quantum theory, what we cannot say in terms of the theory, is not so much that reality is like that, but that the theory is incomplete. Okay, so for example, we know a lot of classical physics. So if we knew how a coin toss was performed, how much force was hit on the coin's mass and mass distribution, where the force was imparted, the amount of air resistance, where it was hit and where it landed, right? Classical physics tells us we can actually predict whether it will land heads up or heads down or tails up. But a convenient theory will say, okay, there's a 50% chance heads up, 50% chance tails up, right? And that statistical theory of coin toss is just because we didn't know all the details about the coin toss. Some variables like air resistance and so on were in a way hidden from us, or because of our ignorance. Okay, so this is the idea of hidden variables that Einstein held, and he thought, okay, quantum theory is just like the coin toss. There's some randomness. That's because something was not put into the theory. So this is a famous picture of Bohr and Einstein discussing, and they had famous fierce debates. And my characterization of their debates is that Einstein tried to get behind this formalism to an understanding of so-called underlying reality. Okay, Bohr had counter arguments centered around incompatible observables, like what we talk about. He didn't quite use this term. He used this idea of complementarity, but it meant the same thing. Okay, and he kept insisting, okay, intrinsically, inherently there's some randomness. His arguments were a bit vague. Okay. So there's a long quote and there's a short quote. I'll just read the short quote. So John Bell said, Bohr was inconsistent. It was unclear, was willfully obscure with terms that were not well defined, like complementarity. But he was right. Einstein was consistent, clear, down to earth, but wrong. Okay. And in this quote, I think Jeremy Bernstein was a physicist who was talking to someone writing a book, writing an autobiography or a biography. He said that he had asked Bell if at that time, he had thought the theory, quantum theory, might simply be wrong, to which Bell had answered, I hesitated to think it might be wrong, but I knew that it was rotten. So very strong words. Okay, this part is titled Entanglement. I think you have all heard of it, 量子纠缠, right? So I'll give you a flavor. Entanglement requires two particles. Okay, let's say two photons, and perhaps just for the sake of argument, these two photons can be in two states, red or blue. Okay, we don't prepare photons in red or blue, but that's just a nice argument. And we can entangle these photons into a two photon state described by this psi in a way that is a superposition of number one being red and number two being blue, and number one being blue and number two being red. Okay, in this way, if you measure number one and you found that it's red, you have collapsed it into this state, the other one must be blue, and the converse is true. Okay, so this is entanglement. So from the spin example in the spin Stern-Gerlach experiment, we can think about entanglement of two spin particles. One in spin up in the z direction, and one in spin down. So A and B are the two particles. You have superposition of up and down for A and B, and down and up for A and B. Okay, the plus and minus don't matter. This is what we call a singlet state. And this way of writing in the Z basis, okay, is an entangled state. You can change to a different basis, right? We call plus and minus, or the X basis. It will also be an entangled state. Okay, so if up and down is a superposition of X plus and X minus, we can re-express this from the Z basis, which is entangled, to the X basis, which is also entangled. So the point I'm trying to make here is the entanglement that is basis independent. Now, so coming back to here, if one is red, then two must be blue. If one is blue, then two must be red. There is a correlation, a statistical correlation, right? It's a one-to-one correlation, right? Okay. So entanglement is really about correlations when it comes to measurement statistics. And these correlations, John Bell tried to explain, it goes like this, right? It's different from correlations we see in our everyday life. He used the example of his colleague called Bertelsmann. So this is probably quite a character. He drew this in his article, I think. He wrote speakable and unspeakable in quantum mechanics. What you can talk about, or what you're forbidden to talk about, like what Bohr is saying. You can't even think about a quantum picture. But this is apparently Bertelsmann in Bell's caricature. He likes to wear, I think, a beret, a French hat. And the thing is, he likes to wear socks that are different colors. So if he goes around a wall corner, and one foot steps out, if you see that this is a pink sock on his foot, the other sock is not pink. Okay, so there will be a correlation. Okay, if you see not pink, the other one is pink. Okay, if you see a certain color, the other one is not that color. Okay, so the correlations from entanglement is actually not the same correlations as the kind of correlations you see in everyday life, Butterman socks, because we can think about entanglement as pink and not pink, okay, or red blue and blue red. Whereas in everyday life, we think about pink not pink or not pink pink on the left and right feet. Okay, let me say that again. So this state is a state where it's 0, 1 and 1, 0. This state in our everyday life is either this or this. So one is an and, one is an or. Okay, and that gives rise to very different statistics. And we'll come back to and or later. Okay. So in 1935, okay, that's 90 years ago, right? 91 years ago. These three gentlemen, Einstein, Podolsky, and Rosen, wrote an article and submitted to Physical Review titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" So they had that hidden variable, the coin toss in mind, right? So quantum mechanics is missing something, that air resistance and analog. In this paper, he argues that there must be two criteria for a theory, right? Completeness, in which every element of the physical reality must have a counterpart in the physical theory. So using the air resistance thing in mind, a statistical theory of coin toss, where you have 50% chance of landing up, 50% chance of landing down, is incomplete because it did not take into account air resistance, let's say, and among other things I mentioned. Okay. And the criteria for theory is that there must be some physical reality that you are measuring. And this definition, which I have actually trouble completely understanding, okay? So I'll give you my best interpretation later. They say that if without in any way disturbing a system, we can predict with certainty, probability equal to 1, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. Okay. So we saw that measurement disturbed a state. If you went from measuring the Stern-Gallac beam in the Z direction and then the X direction. So how can we think about this not disturbing the system? Well, in my opinion, there is physical, according to this criteria, there is physical reality if we have prepared the state in the eigenstate of the observable. Then you get the eigenvalue and the eigenstate remains. Okay, so that's my interpretation, right? Okay, so if you have prepared an eigenstate of the physical observable, you can predict with probability 1 the value of the physical observable. Okay, they assume two things, Einstein, Podolsky, and Rosen, or EPR. One is locality. Let's skip all the words. The other is realism. Okay, we skip the words to try to have a picture in mind. So this is like a video from some years back where the discovery of gravitational waves was very hot. Okay, so there were apparently two black holes. They were rotating and colliding, and we could in the big experiment LIGO, LIGO, could measure gravitational waves. Okay, but what has this got to do with locality, right? So any influence of an interaction, right, has to come from its immediate surroundings, and it will spread out. Okay, there is a finite speed at which a disturbance propagates. That's the idea. It cannot be instantaneous. Realism has the idea that, well, if you measure a pair of red socks, say not measure, but you open a box and you saw a pair of red socks. Before you open that box, that pair of red socks was in there. Okay. In quantum ideas, if you measure a pair of particles and saw that it had these properties, let's say red, then the properties existed prior to your measurement. Okay, that's reality. And that ties in with the very first quote. Does the moon exist if you don't look at it? That's what Einstein asked, right? If you did not look at the moon, you didn't measure it, it must have been there already, right? That's reality. Bohr will go to say that you can't talk about it, and maybe there isn't anything there before you actually measure it. But when you apply it to our everyday experience, that sounds very strange. Okay, yeah, too many words on this slide, but let me give you a flavor. EPR versus quantum theory. EPR is assuming locality and realism. So we call it the local realist. Okay. So EPR is the local realist interpretation of experimental results. Okay. So socks possess a real definite property like red or pink. Or quantum particles possess a real property, spin up or spin down. And that's independent of the observation. When the experimenter conducted the observation, he just uncovered what the property was. Okay, so that's local realism. That's EPR. Standard Copenhagen interpretation. Why Copenhagen? Because Bohr, Heisenberg, these people were in the Quantum Institute at Copenhagen. They say that no truth can be attributed to an object except according to the results of its measurement. So therefore, before measurement, it's meaningless to say what the spin of the particle is. And that's contrary to the idea of realism. Okay, so you can see two schools of thought. Okay, so this is the proposed EPR experiment. Is famous. I think some of you have heard of it. If you understood it, please go along with me. If you didn't understand it or haven't actually had time to go through the details, let me try to explore it with you. So now we have a pair. This is a source, and the source produces a pair of entangled particles. Okay, the entangled particles shoot to the left and to the right, towards two people's apparatus, which quantum people like to say Alice and Bob, A and B. Okay, and this pair of particles, they are entangled. Okay, it could be spin up and down. They have gone to Alice and Bob respectively, or it could be spin down and up. They have gone to Alice and Bob respectively. How do they know? Well, they have that Stern-Gaillard apparatus. Here, Alice has oriented in this way, probably Z direction, and also Bob. And you can get two locations of that particle landing on the photographic screen. If it lands here, Alice will say, I have a result +1. If it lands here, she'll say -1. Likewise, Bob will have two results that he can say 1 and -1. Okay, it doesn't need to be 1 and -1. It's just two distinct results. Okay, 1 and -1, these numbers just give us a nice way of quantifying things. And nowadays we have very good preparation, very good ways to prepare these kind of particles. Okay, let's see what I was going to say. Okay, so yeah, so in this sense, if Alice did the measurement first and she found that it was spin up, we can be sure if Bob did the measurement later, let's say he's a bit further away and the particle reached him later, he will get a spin down. Okay, if they measure it in the up-down basis, because upon Alice's measurement or whoever got the measurement first, quantum theory says, okay, you must collapse the state into up and down, this first one, where Alice got up, Bob must get down. Okay, so quantum theory's measurement postulate says that this state collapses into this. Okay. We don't have a way to describe if there's any time dependence. The best theory so far says, okay, there's a collapse. And according to that collapse, we don't have a time dependence, okay? So it must be immediate. Okay, that's the assumption of the postulate. A postulate is something you cannot prove. You just propose that, okay, let's say if this is true, what are the consequences that arise? So immediate is key here because that kind of violates Einstein's idea of localism. Okay, so EPR's argument on realism says that, well, when Alice has measured her particle to be spin up, right? Without doing anything else that could disturb the system or the other particle, that's the realism assumption, you can predict with certainty that Bob's particle will be spin down. Okay, so why EPR submitted this toy experiment as a model is that, well, there is an element of reality, okay, corresponding to the particle coming to Bob, okay, according to their criteria for realism. Okay, so particle 2 possesses an element of physical reality, that of a spin pointing down. You don't need to measure it. You wouldn't need to disturb it. Okay. But according to the assumption of locality, right? If you place these two apparatus far enough, such that, okay, because Einstein developed the theory of relativity, where no signals can travel faster than light. Okay? If you can separate them far enough so that at the time that Alice measures this particle, any signal will take too long to travel to Bob before Bob gets his measurement. Okay. Then according to the assumption where these two are well separated, they are space-like separated. Okay, if you use the relativity terminology. It cannot be the action carried out in Alice's apparatus that created this element of reality for Bob's particle. And therefore, we must conclude that the particle possessed this said property of spin down before and independently of the measurement of particle 1. Okay, so this is all very logical, and this thought experiment, well, they couldn't do the experiment then. This thought experiment is really well thought through. Okay, so that's a testament to Einstein's genius, actually. Okay, so you can also think about these kind of correlations. If Bob or Alice had a different choice of axis of measurement, so say Bob now tilts his apparatus, so his particle is being measured in the, say, x basis. Okay, but we saw that even if his particle is measured in a different basis, you still get entanglement. So there must still be correlations. Okay, so that's the big idea. Let's not go through the mathematics. Okay, so the argument is that since correlation between different axes of measurement exists, EPR argues that the second particle possesses with certainty the properties of spin up in the z and x directions simultaneously. Okay, it's simultaneous. And this is being rejected by quantum mechanics formalism. You saw that theorem earlier about not having simultaneous eigenvectors, right, for incompatible observables. Therefore, EPR says quantum mechanics is incomplete. Okay, so let me skip all this because I have verbally explained everything. And Niels Bohr in the same year responded with the same title in Physical Review. Okay, nowadays people don't do that. They will just put a post on social media. Right, but in the past it took months to respond. Years. Okay, so Bohr attacks EPR's reality criterion. Okay. So I won't talk about this argument because I don't understand Bohr's argument. But you can see from the earlier quote, how Bohr can be vague. He says that there arises an essential problem of an influence on the precise conditions which define the possible types of prediction that regard the subsequent behavior. Uh, so, and then he talks about no mechanical disturbance. Okay. Okay, I don't do justice to this, but what I'm trying to say is Bohr's counter arguments were rather vague in the sense that Einstein was not talking about a mechanical disturbance from Alice's to Bob's particle. Bohr did not really precisely explain what he meant by an influence or what the possible types of prediction there are. Okay, so to me, it was quite vague. Okay, and in Wikipedia, Rosenfeld, not the same person as Rosen, interpreted Bohr's response. Okay, he was supporting Bohr, I think. Okay, we won't go through this. Okay. So what is science, right? Science is an empirical view of the world. So settle these arguments with a experiment. Okay, so take the same state. Alice choose to measure in the Z basis, Bob measures in the some other angle B basis. And we are then really, okay, I use the spin S notation. Now I use sigma, okay, but it just means spin. We want to calculate from quantum mechanics the expectation value of spin in the Z direction for Alice, spin in the B direction for Bob. Okay. And that can be done because we know how to do matrix multiplications. Okay. So the quantum mechanical expectation value of this quantity. Oh, where did I? Oh, okay, this is fine. Okay, sorry. Okay, it can be measured. Okay, it can be calculated and it can be measured. Let's talk about how it's measured first. Okay. We know these quantum mechanical expectation values. Okay. So this is the representation of what quantum mechanics will predict. The measurement statistics we can also calculate. Okay, so let me explain how these are calculated. They are the same thing, okay, by the way. I just use a different notation because this is from experiment and this is from theory. Okay, so for example, in the first run of the experiment, Alice chose to measure in axis A. Okay, this is a bit small, but let's say Alice has two choices, axis A prime. Bob has two choices, axis B prime. They randomly choose what axis to measure in. They don't talk to each other. So suppose in experiment 1, Alice chose axis A, Bob chose axis B, and these were their results. Okay, 1 and 1. So they just recorded it. So in another run number 2, they chose a different set of axes, and these are their results. So there are 4 possible sets of axis choices, and experimental results are either 1 or -1. To calculate the expectation value of, say, AB, then we look at A times B for every run and average them out. Okay? To calculate the expectation value of A prime B, we look at a whole set of results for A prime B and average them. Okay? So in this case, it will be 1 times 1 plus -1 times 1 plus whatever other set of runs that they did, and then we average. In that way, we will be able to find out the expectation value from experiment of this quantity, right? And because expectation values can be re-expressed this way, right? They're independent. You can calculate each one separately. Okay, there are 3 that are summed up and 1 that is subtracted. Okay, and each of these, if we were to calculate the quantum mechanical prediction, then we can compare. Okay, and in quantum mechanics, okay, the prediction is this, okay, the angle between the choice of axis A and B, assuming that these axes chosen, they all lie on the same plane, right? So it's all in a 2D plane, just for simplicity for our calculations today, okay? So it's all negative cosine of the angle between the two axes of choice, okay? So this is the prediction from quantum mechanics, and therefore this quantity that we can calculate as a theoretical prediction is given by this. Okay, but what about local hidden variable theory predictions? What would EPR say? Well, there are two possible outcomes for each of these choices. It's just +1 or -1, right? For Bob as well, +1 or -1. Okay, if you get +1, you can't get -1, right? And so on. So if A prime plus A, right, is it must be either 2 or -2. Okay, sorry. If A prime and A is 2, then A prime minus A must be 0. That means it's 1 plus 1, right? If it's minus 2, it will be -1 and -1, right? When you subtract, it will also be 0. Conversely, if they sum to 0, then the difference is 2 or -2. In other words, this quantity we wanted to calculate, local hidden variable predictions say that, okay, you can factor them, right? And this would be either 2 or -2. If that's the case, this is 0. Then B could be 1 or -1. So in that scenario, this gives me +2 or -2. The same thing goes here. If this is 2 or -2, A plus A prime is 0. Then you're left with this surviving term. B prime can be 1 or -1. You still get the same set of results, 2 or -2. So on average, therefore, you will get between 2 and -2. Okay, but where is this so-called local hidden variable inside here? This looks like just some normal algebra, logical, mathematical calculations. Well, quantum mechanics says actually you can't think about A plus A prime because it's not even possible to measure A and A prime simultaneously. So thinking about A plus A prime being 2 or -2 is actually impossible in quantum mechanics. You cannot hold that picture in mind. Likewise, B and B prime, okay? And by assigning these outcomes to the complementary observables A and A prime to get this, you are assuming that these properties exist independent of the measurement. Okay, so that's the realism assumption. How about so realism is like hidden variable, okay? I have used realism and hidden variable interchangeably. How about locality? Well, we wrote this out and then we factorized it. The factorizability condition where A and B are factorized into average of A times B is factorized into average of A times average of B implies that the probability of getting the outcomes A and B are independent of each other. What is measured at Alice's detector does not affect Bob's measurement and vice versa. Okay, because they are space-like separated, they are then independent because nothing happens instantaneously. Okay, yeah. EPR argue that someone else making a measurement shouldn't be able to change the probability that I will find something if you are Bob. Okay, so you have two predictions from local hidden variable theory or local realism. It must be between 2 and -2 on average. And from quantum mechanics, you get this, okay, more complicated looking expression. So very good, right? I mean, you have how to calculate this quantity in an experiment, what quantum mechanics predicts for that quantity, and what Einstein EPR would have predicted for that same quantity. Okay, so this was all done by John Bell. Okay, and therefore, this inequality, where you take the local hidden variable prediction and average it, the average must fall between the two possibilities. 2n minus 2. Okay, and this is called Bell's inequality. There are many versions. This is the so-called CHSH after the 4 people. Forgot their full names, but CHSH version. Okay, so this is excellent. So Bell had put what was a philosophical argument between Einstein and Bohr and made it into a scientific argument where you can check with an experiment. Okay, and the experiment is like that, right? So I have put this Alice, this is Bob. I have put all the choices on the same plane, right? And they are now separated by the same angle. So angle between A and B is theta. Between A prime and B is also theta. A prime B is theta. But between A and B is 3 theta, right? And the quantum mechanical prediction is that, it will look like this, the blue curve. The hidden variable, local hidden variable or local realism prediction from Einstein is that it must lie between 2 and minus 2. So here is where quantum theory can be falsified. Okay. Yeah, and okay, I mixed up the slide, but the experiments show that indeed quantum theory is correct. Okay, and Einstein was wrong because you get experimental results in this range where Bell's inequality was violated. Okay, so John Bell died in 1990, and now we know Bell's theorem that no physical theory of local hidden variables can reproduce all of the predictions of quantum mechanics. So this is quite a subtle way of putting that. Okay, but because the Bell tests or the Bell EPR experiments, right? They rule out theories that are local and hidden variable. Now people are looking for theories that are non-local but also hidden variables. Okay, or local but no hidden variables. Okay, but that's quantum mechanics. Okay, so this is the picture that we have now, the best picture, that reality cannot have both elements of locality or localism and hidden variables or realism in Einstein's words. So the question of whether the moon looks at it, whether the moon exists if you don't look at it, still exists. It's yeah, it's an interesting question. Okay, so the landmark experiment is by Alain Aspect. Okay, so he found a violation of Bell's inequalities. He wrote it in a different form, so it's between -1 and 0, but that's the same idea. Okay, and for that, these 3 gentlemen, Aspect, Clauser, and Zelinger, got the Nobel Prize 4 years ago. Okay, and then there are loopholes, right? I won't, in the interest of time, because I've still got a lot. I'm only halfway through. In the interest of time, there are loopholes. The locality loopholes means that you must have space-like separation that's done. The fair sampling loophole, I wrote unfair, which I prefer, but it's actually in standard terminology called fair sampling loophole. It's kind of like a conspiracy theory because these photon detectors are inefficient. What if because you only collected a fraction of all the photons possible, you get a bias sample, and maybe this bias sample always shows a violation. If you had collected everything, then maybe you realize that, okay, Bell's inequality will be respected. Okay, so people try to close the fair sampling loophole by having more and more efficient detectors. Another is the memory loophole, that you assume that every round of a test is IID, right? So statistically independent and identical. Okay, so I won't go through this. The most interesting one is the free will loophole, sometimes called super determinism loophole or skepticism loophole. What if the results were fated? We are following a script predetermined by God, fate, universe. We have no free will. So all these detectors conspire or are correlated with events in the shared causal past. Okay, some correlations happen in the past to give you violations. okay, including the physicist running the experiment who does not have free will. This we can, of course, never close, and we can think of a shared causal past if we believe that the universe began from a Big Bang. Okay, we all started from there. So perhaps this is the ultimate question. Okay, but I think this is uh, fun to think of, but not meaningful to try to close this loophole. Okay. So some experiments, I'll skip this, okay. And the first loophole free Bell test was performed in 2015, some 11 years ago already, in Netherlands, Delft. Okay, I'll skip these as well. Okay. We haven't finished all the questions. We have tried to answer some questions. I will try to go back and help you recall what questions. Give me a second. All right. So what is this picture of the physical world? Yes, I think we have had some idea, right, from Bell's theorem. Um, but is there something deeper, because we haven't resolved the Schrodinger's cat problem? Okay, so we are going to try to do that with the idea of decoherence. Okay, but before that, we have to talk about a bit of mathematics or a bit of formalism called the density matrix formalism. Okay. Uh, Now it's I've already talked for 1 hour 20 minutes. I still have a lot to say, but I think we should take a short break. Let's take a 3-minute break. Okay, and come back at 11:25. Okay, so when we come back, we'll talk about the density matrix formalism and the idea of decoherence. And I'm going to have to go through very fast. Okay, see you in 3 minutes. Okay, I'm back. It's 11:25. We should continue. Um, I should warn you that I think I might have to go longer than 2 hours because I'm still only 2/3 of the way through. Okay, but I'll try to give you a flavor of everything I want to say without too much going to detail. Now, we talk about quantum information, and in information theory, there's the idea of a bit of information. And then in the quantum version, we need to know what is that bit of quantum information. And that is usually defined with the density matrix in mind. Okay, so that's why we are going to detour into a bit of formalism, uh, general ideas without um, technical details. Okay. If you know who Claude Shannon is, he's the father of information theory in computer science, and von Neumann of the measurement postulate, right? Um, Told him he should call the idea of the amount of information entropy for two reasons. In the first place, the uncertainty function has been used in statistical mechanics under that name, so it already has a name. In the second place, and this is so funny, more important, nobody knows what entropy really is. So in a debate, you will always have the advantage. So I don't know if this is advice for a young scientist, but I think it's counter advice. I think take this with some humor. Okay, what is a density operator for a pure state, right? We wrote the state as in Dirac notation as a cat. Okay, so the density operator is just the outer product of this cat. Okay. So if the cat were written in a different basis, right, then your density operator is just this. Okay. So what we can then see is that since this represents row and this represents column, if on the diagonal when I equals to j, you get I CI conjugate. So this is a probability as we saw. So the diagonal terms on a density matrix or density operator represent probabilities. They are real and they are more than 0, less than 1, or more than or equal to 0, less than or equal to 1. The off-diagonal terms, where it's not row and equal to column, I not equal to j, we call it interference or coherence terms. Okay, so this will be important later on. Okay, because we are going to talk about the picture of quantum world, and we are going to use the idea of decoherence, loss of coherence. Okay. Yeah. Okay, let me skip this. What I want to say is we can calculate expectation values as well with the density matrix. TR means trace. Trace means the sum of the diagonal terms. Okay, let me skip the technical details. Oh, maybe not. So this is kind of like the proof that the trace of the density matrix times the observable, it's supposed to give you the average value of the observable. Okay, if you go through this set of derivation, you will find that there exists in the last step this inner product between an eigenstate, the ith eigenstate or eigenvector of the observable A, and the state you have in mind. Okay, this we interpret as the probability of outcome A, and it arises from the Bond rule. Okay, so it's applying Bond rule. Okay, and when you apply that, you will be able to say that, okay, the trace of this product of rho and A gives you the expectation value of A. Okay, keep that in mind as well. Okay, but this is a pure state. Okay, this is a pure state. The system exists in this state psi. We can think about a general state. It doesn't need to be a pure state. A general state is a statistical mixture of pure states. For example, each of these particles in this collection are pure states. Spin up, spin up, spin up, up, and then the orange ones are down, 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 down. And this is 50% spin up, 50% spin down. I can also describe this with a density operator. And it's different from a particle being in a superposition of spin up and down. Okay. So the way to describe this is with a density operator. As I mentioned, the diagonal terms are probabilities. So there's 50% of up, 50% of down. So these are also diagonal terms. Okay. So we then can generalize the postulates of quantum mechanics to include what we now call mixed states. Okay, and mixed states can only be described by density operators, not by a Dirac-Ket notation. Okay. Okay, so the key result that I want to impress upon you here is that information about the observable A is all contained in the reduced, information about a system A is contained in the reduced density matrix of A. Sorry, I'm rushing a little bit. Okay, no. Let me show this later. Okay. I mentioned that you need to talk about density matrix to think about the idea of information. So let's talk about classical information first, where it's defined by Shannon entropy. So as an example, I have a 6-letter word here. If I ask you to guess the first letter, I actually wanted this to be interactive, but I think I don't have time. Then if you just did a random guess without knowing about the frequency of occurrence of first letters of 6-letter words in English, then your probability is 1/26 because there are 26 letters in the alphabets. If you knew more about the occurrence of first letters for 6-letter words, your guess will be better because you will have then idea of all these probabilities, right? Now I'm going to tell you what's the first letter. Q. Okay, then now you have suddenly a lot more information because you can then look at 6-letter words on the internet. Okay. You're now asked to guess the second letter. Okay, no, you just look up a lot of 6-letter words starting with Q. There's quartz, queens, quirks, Qatari, Qigong. So then you can therefore narrow down what is a more likely second letter, right? Okay, now suppose I tell you the second letter and the third letter is Q, U, and A. Then you start to be able to get more information, right? You can strike out a lot of things, a lot of words. Maybe quartz is one of them. So what do you think is a likely fourth letter? Put your guess in the chat. It'll be interesting to see your guesses. So I'll pause here for a minute. You can type into the chat. R, yeah. So there's a guess, there's R, right? But okay, but it's more than just quartz, right? Any other guesses before I continue? Okay, maybe you're too shy to guess. Okay, never mind. I have this in mind. So this word is quanta. Okay, quanta, because we are doing quantum theory, right? So why did I do this, right? When you are guessing, you get some information every time one of the letters appear. And the amount of information you got was actually how unlikely that letter was, right? So Q was very unlikely, right? And then you realize, you got a lot of information then. But once you got to Q, U, A, and T, let's say, the probably the only possibility was A. So even if I told you A, you knew it was going to be A, it was very likely to be A, or could be S, I guess. The amount of information you got was very little. So there is a bit of information that is in every letter, every subsequent letter. And that amount of information is related to how unlikely the letter is, or because probability of the letter occurring is how likely it is, we can think of it as 1 over the probability of the letter occurring, right? So 1 over P. Okay, so classical information is defined as in some base, like log base 2 of 1 over P, or you can think of it as negative log base 2 of P. Okay? When P is half, right, because P is a probability, then you get 1 bit of information. It's either black or white, let's say. Okay, you can do a log of negative log of half is 1. And if you average over the amount of information you got from here, right, or the average over the amount of information you will have to sum up over the probability of getting one of these letters X times the information you got in each letter, then this is Shannon entropy. Okay. Now, this digression about classical information leads us to von Neumann entropy. Okay, so von Neumann entropy, let me just skip this. Okay, there are too many S's around. Spin was S, I think CSH inequality was S. Von Neumann entropy is also S. It's defined in terms of the density operator, where let's look at this definition. It's the eigenvalue, okay, is rho log rho, taken a trace of, but when you do that, it's the sum of the eigenvalues of the density operator log base 2 of that eigenvalue. Okay, and remember the eigenvalue exists on the diagonal, which means it's a probability as well. Okay, so it's the sum of the probability of this bit of information. So this von Neumann entropy, as it is defined, is a measure of the informational content of a quantum state. Okay, it can go from 0, so a pure state, you just know what it is. There's no surprise, to a mixed state, okay, which you are not sure what it is. So there is a lot of surprise if you find it. Okay, now it looks like there are bits and pieces of things here and there. We are used to thinking about a quantum system and describing it with the Hamiltonian. But actually, in reality, the system must interact with an environment that we actually have no access to. We don't measure it. It's too large, too many degrees of freedom. We don't have information about it. But if you think about it, the full Hamiltonian must involve the system Hamiltonian, environment Hamiltonian, and the interaction between the system and the environment. Okay, are there such quantum systems? Yes. Now, okay, let me just use this one as an example. This is because I think you guys are Xidian, right? Electrical engineering. I don't know if that's true, but I'm interpreting your university name as you guys being trained in engineering. So these are metal gates on semiconductor substrates where you can isolate individual electrons. So here, this is just a cartoon. And you can manipulate them with, say, ESR, basically a magnetic field, and so on. These don't exist in isolation, these systems, right? They will interact with the environment. That's how you can manipulate them. And for example, there must also be spins in the substrate that interact with your electrons, right? Those are the environment spins. And as a result, this is an open quantum system, okay? But typically, if it's well constructed, well engineered, the interaction with the environment is weak, or it can be turned on and off. When you don't want it, like for example, you don't want to manipulate it, you kind of turn it off, okay? Okay, so there are two parts to this entire quantum system, the system and the environment. Okay, so you can think of them as subsystems of the full thing. When one subsystem is not accessible, say the environment B, okay, you can only make measurements on A, okay. So let's skip all of the mathematics. The expectation value of the observable only depends on the density matrix of A. Suppose the observable is that of A, okay? So all of the information content is is encapsulated in row A, density matrix of A. Okay. And what are we taking the trace over? We're taking the trace over the density matrix of over the subsystem A. Okay, I'm not making just doing justice to this, I understand. But let's just prioritize going through the concepts. Okay. Yeah, so this is exactly what I said. How did we get to just getting the subsystem A? Was we did a partial trace over subsystem B, right? So here we started with the full system. We averaged out or partial traced out all the degrees of freedom of B. And then we say that from this result, all the measurement statistics of an observable of A is encapsulated in the reduced density matrix of A. Okay, so all we need to know is just A. Okay. Okay. But there is an issue when you do a tracing out of a subsystem B. Okay. So this is the reduced density matrix after you have done a partial trace. And it is, again, a matrix with ith row, jth column. And in the ith row and jth column, you get a complex number related to the eigenvectors of B. Okay. Now, these are two eigenvectors, the Bi and Bj. Okay. If this overlap or the inner product is 0, then your reduced density matrix is completely diagonal. If it is non-zero, then there are some off-diagonal terms. Remember, we talk about off-diagonal terms, we call it coherence. Okay? Yeah. So, so this is key, right? If B was your environment, something about the environment that you don't know when you trace it out, okay, affects what you can know about your system. So that's the idea. Okay. And if this overlap is 0, then your system is purely diagonal. There are no off-diagonal terms, then you don't have coherence in your system. Okay, that's the conceptual idea. Okay. So I will try and tie that in with Schrodinger's cat soon. But first, I want to talk about the classical and quantum origin of mixed states. We had this picture just now of a mixed state, okay? And we say, oh, think about a mixed state as a statistical mixture of pure states. But due to ignorance about which state is in what particle, right? We use the density matrix idea to describe it. Okay. But now, knowing that when your state could be made just purely diagonal based on your what's in the environment, right, from the partial trace, there is such a picture of a improper statistical mixture, where if your system gets entangled with the environment, okay, or your system A with environment B, or S with E, then when you only find out about the state of your system through the reduced density matrix by tracing out the environment, then it will be mixed. In other words, you will only get diagonal terms. Okay, there's no coherence in your system. So it reflects a loss of information about the composite system environment state. And this mixture arises from entanglement with the environment. And therefore, this is quantum in nature. So this view of mixed state, okay, versus this view is a classical versus a quantum view, right? So even though I asked you to have this picture in mind, actually this is the correct picture, all right? Because this one is really a product state of pure states. Okay. So let me skip this. You can rewrite the postulates of quantum mechanics now in density matrix formalism. It's just details that are not so important, right? So for example, the dynamics postulate tree, how the density matrix evolves with time, and how the density matrix collapses, the same ideas as before. Okay, so this idea of decoherence, right? So Abraham Pius was was a biographer of Einstein. Had many discussions with Einstein. He wrote, I recall that during one walk, Einstein suddenly stopped, turned to me and asked whether I really believe that the moon exists only when I look at it. The rest of the walk was devoted to a discussion of what a physicist should mean by the term to exist. Okay. So a recap of the Copenhagen interpretation, right? Initially, there were difficulties with quantum mechanics with the complex numbers. Resolution was to take the mod square, okay? And that's probability density. Initial difficulties were two contradictory accounts, wave and particle. Boss complementary principle kind of say, you can talk about about them, but not simultaneously. And then there was a disconnect between quantum theory and classical theory predictions, and Boss said, there must be some correspondence in some limit. Okay, but this is really very fuzzy. Nobody can really rigorously say this. Okay, this complementary principle is just I feel language. Okay, the only more firmer mathematical resolution is this one. Yeah, okay, complementarity, you can think of this as yin and yang. And correspondence, again, this is a very cute cartoon. There's a quantum world and there's a classical world. We don't really know in what limit, whether H goes to zero Planck's constant, right? You cross from quantum to classical, right? The so-called quantum classical transition. Okay, so the measurement problem remains a problem in quantum mechanics, right? And the problem is this: there's a core tension between two incompatible rules in quantum postulates. Time evolution is deterministic and unitary. Can go forward and backward in time. You can calculate that. Wave function collapse is probabilistic. It's not unitary. It's not linear. Okay. Time evolution is also linear, by the way. So some people try to resolve this, right? Some attempted resolutions was von Neumann's model of measurement, right? You accept that there are two incompatible rules. It becomes a postulate. So no need to question, just accept it. David Bohm was one of those that did not accept it, and he tried to find, he came up with a non-local but hidden variable theory. In this theory, there is no randomness, okay? We see randomness in the results of measurement because we did not know about Bohm's pilot wave. So for example, this is a quantum particle, it's moving. And why did it move to a certain place is because there is a so-called pilot wave guiding it. Okay, so this pilot wave exists at all places at the same time. Okay, if a disturbance happens here, it is felt everywhere. So it's a non-local theory. The pilot wave is the hidden variable. Okay, people didn't like it because people think that Einstein's relativity should hold and non-locality conflicts with relativity. But it was a very brave and very scientific attempt to try to get to the bottom of a theory, right? Now the modern consensus is decoherence, arguably, although there are many worlds, multiple universes is still very popular. And this was developed by Zay, Jules, and Zurek. So this is Zay, just over, I guess, 60, 70 years ago. Okay, so what are the measurement problems? I'm going to use this breakdown of the measurement problems into three parts, according to this person called Schlosshauer. He wrote a very good textbook on this. And the problem is epitomized by Schrödinger's cat. It refers to the cat being dead and alive but the collapse is into the cat being alive or dead upon observation. Okay, so this dead and alive, right, is why is it so hard to observe interference, right? Because you have interference when you have a superposition. Okay, so that's the first problem. Okay, so for this is like the double slit experiment. Okay, let me skip all the words. Okay, the second problem is the problem of the preferred basis. Because what singles out some preferred quantities. So for example, you see if you say measure a molecule in a certain position, it's usually going to be in a definite position rather than a superposition, which is just related to the former by a change of basis, right? For example, a definite position is a superposition of many different momentum states. Why is position preferred whenever you measure something, look at something, rather than momentum, right? And finally, the Schwarzschild breaks it down into the third problem, the problem of outcomes. Why do measurements have outcomes at all? And what selects a particular outcome? Okay, so I with the double slit, right, you probably have seen before. This is the YouTube link, but I can't show you. There's not enough time. So a double slit experiment performed by Hitachi several decades ago, that the electrons one at a time, so it's a single electron experiment, land on the screen through a biprism or double slit, and it looks random, but over time it builds up into the interference pattern. So what is interfering with what? I don't have a single electron thing and don't even have single particle equipment, but if you can get your hands on a precision instrument, right, like a single photon sensitivity CCD camera, we all have laser pointers. You can put many polarizing filters together. You can come up with something similar. Okay, so my homemade experiment at SPMS, School of Physical and Mathematical Sciences at NTU, also gave me something similar. Okay, I want to tie this with the loss of coherence. So allow me to introduce more basic stuff. If you have a double slit experiment, you get a interference pattern like this if you think classically, right? Either the particles enter from the top or the bottom slit. But if you think quantum mechanically, they can interfere, as you know from physics, and you get interference patterns. And that's exactly what we saw, right? So if we ask the question, which slit did the electron pass through, then you need to detect the electron behind one of the slits. How do you do that, right? Maybe you can think about shining a light, okay? But when you shine light, say behind one of the slits, then you lose the interference pattern and you get classical pattern now. Okay, so asking the question, which slit did the electron pass through, you kind of disturb the way it passes through. Okay, and when you decrease the wavelength of light, you're getting more and more smeared out, right? Then I think it's increasing. You're increasing the uncertainty. Oh, I'm sorry, this is correct. Sorry, increasing the certainty by decreasing the wavelength. Then you get more and more of a classical pattern. Okay, so how do we see this in a quantum treatment, right? So if I want to talk about the electron's probability density, right, it is originally in a superposition of passing through slit 1 and slit 2. So if you do that, right, carry through the calculations, the probability density is mod squared of that in the, say, position basis. So that's why there's an inner product with X. Then you get three terms, right? This is the classical distribution, and this is the so-called coherence term. This is the off-diagonal term. Okay, then we can explain how the coherence decays about observation of which path using von Neumann's model of measurement. Okay, so von Neumann's model is this: the system and apparatus are both treated as quantum systems. The system starts in some state, the apparatus starts in a ready state, hence the subscript R. When there's an interaction, the apparatus faithfully records what the system state is in. Let's say system is in the ith state, the apparatus will go to the ith apparatus state. Okay, so this is a toy model, is an idea, von Neumann's measurement scheme. It's a quantum non-demolition measurement. It doesn't perturb the system. And post-measurement, you collapse the system state. Okay, so suppose we get this von Neumann measurement being applied to the apparatus and the system. Having passed through slip 1, right, the apparatus goes from ready to recording the system as having passed through slip 1. And likewise, having passed through slip 2, the apparatus goes from ready to seeing that the system passed through slip 2. It records faithfully. Right? The particle wave function is a superposition of going through 1 and 2. And then post-measurement, you have an entanglement, right? This is now an entangled state between the system and apparatus. System in 1, apparatus in records in 1, system in 2, slip 2, apparatus records that faithfully in 2. But when you want to get the reduced density operator of the particle, you need to trace out the system, I mean the apparatus. And when you do that, I'm skipping all the math, right? You get this particular term. These two terms are your classical distribution. This term contains the overlap of the apparatus pointer states. Remember, we talked about overlap several slides ago. And if the overlap is 0, then this term, which carries the interference pattern terms, right, becomes 0. So if this term called the overlap of the apparatus pointer states is non-zero, then you still get interference on your screen. So what does that mean? The visibility of the interference term depends on the overlap of the detector states. If you're able to perfectly distinguish whether the particle was here or here, because you increase the certainty of your electron position, then interference disappears because the overlap becomes orthogonal. But if you can't really distinguish, maybe you use a very long wavelength, so you can't quite tell if the particle came from 1 or 2. They are still here. You recover the interference. So the intermediate case is most likely the case. They have damped interference, but not complete. So the idea then, when you talk about an open quantum system where you have system environment or system apparatus, now using all the machinery of quantum mechanics, you can arrive at this entanglement between system and apparatus, and just using the quantum mechanical rules, also recover the idea of complementarity that Bohr very fuzzily introduced. It is then a consequence of quantum entanglement, okay? Where you either see wave or particle, quantum or classical interference. Okay, so the problem of interference being very hard to observe can therefore be resolved, right? Because you don't need to have an apparatus doing the measurement. Your system is already, your environment is already constantly monitoring the state of the system. Okay, the environmental monitoring process does not require a human observer, and the fact that which state, right, slip 1 or slip 2, can be encoded into the environment could in principle be read out. We don't even need to read it out in theory, just in principle. It's sufficient for the interference pattern to disappear. Okay, so recall the weakness, say you need consciousness and all that. No, actually, in this way of looking at things, you just need to enlarge your system to include the environment. Okay, we'll skip this. The time scale of this so-called decoherence is actually very short. It was calculated by Jules and Zay in 1984. Okay, then what about the preferred basis problem? Okay, so this is now a bit hard to talk about actually, if I were to actually speed things up. But let me try to give you a flavor. Okay, or maybe I should skip a little bit. Okay, I will get to the result instead of going through the all the arguments. Okay. Okay, maybe we should look at the arguments. Okay, so again, we look at a system environment or system apparatus interaction. Let's say we are looking at a single spin. The spin could be up or down, right, or 0, 1. And then the apparatus measures it faithfully in that, so in a certain basis, right? Okay. If you then have a superposition of your system, then you get the system apparatus being entangled. Okay. But as we saw earlier on, this entanglement can be expressed in different bases. It will still be entangled. Okay. So what we have to say here is that, well, the apparatus seems to be recording the state of the system in the Z basis. But because it's just a mathematical change of basis, you can write it this way, express it in the X basis, and you then should also be able to say that the apparatus measures spin in the X direction. And this is a problem because these two system and apparatus states are allowed by the formalism of quantum mechanics, but you cannot, if your apparatus is very big, you need to change direction of the orientation of the apparatus in order to go from here to here. It's not a mathematical change. And it could, in theories, be said to measure non-commuting observables, X and Z, simultaneously. So there's a problem, okay? And it contradicts our experience, right? Your measurement device, you have to really change the direction to say measure Z or measure X. So the preferred basis is not explained by this von Neumann measurement scheme, okay? And then what the central question is what singles out the particular superpositions. Okay, I'm going to go over time, so if you could bear with me for another 15 minutes, I think I should be done. So the idea is this, right? Now we change system apparatus or system apparatus environment to just system environment. Okay, so everything remains the same rules of measurement, but this time we think about the environment as measuring from the ready state 0 to the state, all right, of the system 1. Okay, so again we have say superposition state for the system, and then the system environment interaction results in entangled states between system and environment. Here we have two states of the system, the plus state and the minus state, right? So then the entanglement state also has the plus and minus. And you can actually write these in infinitely many bases. You just need to go from basis E to basis E prime, okay? Psi to psi prime. Okay, then now with this set of rules of how the environment measures the system, then let's consider a different superposition of the system phi, right? Which is the superposition of psi plus and psi minus. And going by the same rules, right? The environment will measure actually E1. Environment is now in a product state with the system and not an entangled state. Okay. And why is that so? Well, because psi or phi rather, which is a superposition of plus and minus, if you had added them up, it's just psi 1. Okay. So why do we get a product state in one interaction and an entangled state in another? Is because of the rules of interaction between the system and environment. So not all superpositions are equal. Okay. Right? You get a product state, you have no environment overlap terms that causes the loss of coherence. And that comes from the particular form of the system-environment interaction that determines whether the environment is sensitive or not to the difference between system states. Okay. So what are we trying to say, right? We are trying to say that there are certain types of states of the system that are robust against decoherence, and certain types and then these are the ones that are least entangled. Okay. Okay, and that comes from the interaction. If the interaction were if the interaction is such that the environment measures the position of the system, then a superposition of position states, okay, then becomes prone to loss of coherence. Okay, you cannot see that kind of interference. Finally, the problem of outcomes. Okay, why do measurements have outcomes at all, and what selects a particular outcome among the different possibilities described by the distribution? When we measure, we only get one result, a definite result, a value. We don't get an indefinite result, a superposition. In fact, you can't imagine what it is for an apparatus to record one and zero. It's just one or zero. The standard quantum mechanical prescription is that the outcome is an eigenvalue and the system ends up in an eigenstate. It doesn't explain anything. It just tells you that's how it is. The decoherence framework cannot solve this problem because the process is like this. This decoherence is such that you have the interaction between system apparatus and environment, leads to entanglement. Superposition persists from system to apparatus to environment. And because we don't know what is this, we can't have access to environment, too many degrees of freedom. We don't have any knowledge. Quantum mechanically, that means we trace out the environment and we get a reduced density matrix of the system. Okay, and then it's generally a mixture. Okay, and mixture tells us only classical probabilities. Okay, so that's the decoherence framework. It still requires the collapse postulate. It cannot distinguish between ensemble of pure states or a mixed state arising from tracing out the environment. And this tracing out the environment, partial trace, as we saw earlier, relies on Bond rule. And Bond rule assumes measurements have outcomes with probabilities. Therefore, if you were to ask the question of why are there outcomes with these probabilities, decoherence already assumes this Bond rule. It therefore cannot answer it, right? Because that will be then a circular argument. Okay, so this is still, this problem of outcomes is still an open question. Why it's powerful? It's because it explains how quantum interference of an open system decays, leading to the appearance of classical properties, right? Why your double slit interference disappears when you have, say, instead of a vacuum, an air chamber. And it tells you that interactions with the environment induce a system basis that can be robust or not robust against environment observing or monitoring your states. And therefore, it tells you when you know the interaction between system and environment, what the pointer states are, or the preferred robust states are. Okay. So perhaps that kind of answers Einstein's question, but because there are always photons in the universe, there's a cosmic background radiation. The interaction of the photons with the moon is such that the universe environment is always observing the position state of the moon. All right, you don't need human consciousness in principle, as long as the universe can detect the position state of the moon, it will collapse into that state. Okay, so let me skip these things. They are not so important. Okay, but then this, okay, I am almost at the end. Now I'm at 112 slides. So this von Neumann chain also has its critics. It is kicking the can down the road. So again, John Bell drew this sarcastic cartoon. So you have the double slit experiment. So this is quantum. What lands, the electrons or the photons land on the screen. Then the photographic spots on the screen is the measurement, irreversible new information, because irreversible because it's measurement. So you kind of split this into quantum and this into classical. But if you think about the screen, there is a photographic plate, it's made of, in the era where you have film, right? Made of chemicals, atoms. That is also quantum. So maybe the split is here. This is quantum. Your human observer is classical. But then our eyes also have a retina, and it's made of a collection of rods and cones. Maybe you should think about that as quantum mechanical. Maybe the split is with the brain, but then you go the same route. The brain contains neurons and so on. Maybe it's with the mind. So really, he's making fun at von Neumann chain of measurement, because von Neumann didn't care where a record of measurement became classical. So it's still a question: is this fourth postulate of measurement really correct? Okay, so this is all I'm saying in words. Let's skip all the text. And so all this, if you found it interesting, was very difficult. Zay in 1970 wrote this article on the interpretation of measurement in quantum theory. And I've always felt bitter about the way Bohr's authority, together with Pauli's sarcasm, killed any discussion about the fundamental problems of the quantum. I expect that the Copenhagen interpretation will sometime be called the greatest sophism in the history of science, but I will consider it an terrible injustice if, when someday a solution should be found, some people claim that, this is of course what Bohr always meant, only because he was sufficiently vague. Okay, we are a long way from there, but this is still very valid because we are a long way from a solution to the measurement problem, even though today we have noisy intermediate scale quantum processors. For this paper, one referee wrote, "The paper is completely senseless. It is clear that the author has not fully understood the problem and the previous contributions in the field." With that, the historian of science, David H. asks Zay, "Do you feel that physicists whose hold unorthodox views about quantum mechanics have any great difficulties in carrying out their work?" And this is Zay's reply. Okay, I hope I have given you a flavor of the kind of questions, foundational questions, we have tried to answer, because those are important. Because if we don't try to answer them, quantum technologies, or what we know as quantum information science, stand on a foundation of sand, right? So I have talked about Bell's theorem and Bell's test. I've talked about the measurement problem and von Neumann chain. Those are decades ago, yet today we have a lot of companies on quantum computing and so on. So perhaps quantum is useful, money-making, important, but we still have problems understanding it. And for today, I'll leave you with this quote by George Box. I did my PhD at University of Wisconsin-Madison. He said, all models are wrong, but some are useful. And you can see that with the proliferation of quantum technologies companies, quantum mechanics is indeed very, very useful. Okay, with that, I thank you, and sorry for keeping you a bit longer than I expected. I'll stop the recording here. If you would like to ask